So finite elements starts by approximating the function restricted to what's called the linear space of functions. So let me give you an example. Can you tell me that in this example, what do you think? In this example, I'm trying to approximate this weakly function as precisely as possible, right? So what do you think is my constraint? What am I allowed to use to approximate the weakly function as close as possible so that I got this result? Why cannot I get any closer? Yes, here one thing is obvious is that I'm actually constrained to use a linear function per element, right? So actually in this case, this is the only constraint I have, okay? Now, we need to take that constraint and now ask the question, what does that constraint give me? Why am I using that constraint at all? Why am I constraining myself at all? It's because there are less functions that satisfy this constraint than functions that does not satisfy the constraint, right? If you don't have the constraint, you have just too many functions to choose from. But if I have this constraint, I actually are working in a very, very manageable space. All the functions I can choose from in the space of piecewise linear functions is actually finite dimensional. It's not finite, but it's finite dimensional. I can map all possible functions like that, one-to-one, to the space of 20-dimensional numbers. So if I have a 20-dimensional vector, okay, the space of all possible 20-dimensional vectors is actually the same as the space of all such functions. Okay, so what finite element does is that it restricts myself into a function space that is much, much more manageable than the space of all possible solutions. And then figure out this one-to-one map between this much smaller functional space and a space of numbers, because the space of numbers is what computers can deal with. Okay, and then rewrite the problem of the differential equations and weak forms as equations for these numbers, these 20 numbers, and then use computers to solve these equations for these 20 numbers. And then use the inverse of the map to map from the 20 numbers, which I get as my solution, to a function like that. Okay, so that's kind of the overall strategy of finite element. Yeah, question?
Well, I'm just wondering, this seems like one of the more computationally heavy versions that we've looked at so far. Did anyone use this before computers?
Did anyone use this before computers? I think there is. Actually, the history of finite element is as old as electric computers. So I mean, you all know, like electric computers are developed during World War II, right? Actually, 3 different countries are doing pretty much very similar things, but for very different applications. The US is doing this because there are not enough people to compute trajectories of shells for the Navy. So the Navy really wants to build a kind of a automatic version of computers, which was humans, to accelerate these calculations. Now the UK is also doing the same thing, but for the purpose of decoding the Enigma, which is used as a communication protocol for Germany. So they want computers that can crunch a lot of numbers to decode their messages quickly, okay, as opposed to have just rooms of people doing calculations. And actually, Germany is also doing very similar things, but their application is actually in how to build airplanes. Germany has built several airplanes in World War II that has structural problems one way or another. And being able to calculate in various loading conditions how the structural deformations of airplane is going to go, it's a very tricky question. Especially Germany is one of the first countries to find problems relating to aeroelasticity. So aeroelasticity is basically the deformation of the structures is going to make the loading on the airplane, the aerodynamic loading, to be different, which is going to cause the loading to be deformation to be even more different, and the aerodynamics to be even more different, and this kind of creates a chain rule that can basically break the wing of airplanes. And so to predict things like that, they need a lot of calculation. And I'm pretty certain finite elements is actually used at that time to calculate deformation of airplanes. So without having electric computers. And what you said, I don't think is actually true. It's not really one of the more computationally heavy versions. It can be computationally very efficient. It's just one of the mathematically more heavy aspects, right? I mean, you need a lot of derivation to figure out what are the numbers you need to crunch. But it doesn't necessarily mean there are more numbers you need to crunch. It can well be the opposite.
Yeah, it's not necessarily. It doesn't seem to be a very iterative method.
Right.
As far as all the other ones, it was just crunch the space, crunch your cells smaller and smaller, iterate more. I guess this one also does that.
This one also does that, but you have a little bit more control on, especially when you have different, very inhomogeneous structural properties, right? I mean, you put wood on steel and things like that. Using other methods, it's not really very obvious how to deal with the interfaces. With finite elements, it's very, if you have wood in one element, steel on the other element, is very obvious how to deal with that in finite elements. Okay, let's see, I have an hour left. So, right, so let me first explain how the mapping works. How do we map a space of functions to a space of numbers? Because that mapping is used twice. Once to go from the equations as written as a weak form that involves integrals and derivatives into equations that involves only numbers. Okay, and then it is used again as the inverse. Once we have the solution, we have to go from these 20 numbers to a solution that actually looks like a function that describes the deformation. So let's describe the mapping first.